Hello everyone and welcome to another Advanced High Maths video lesson on differentiation. Today what we're going to do is take a wee look at higher derivatives and apply them to stationary points and rectilinear motion. The success criteria for this lesson is quite big. We're going to go through the Leibniz and Newton notation for higher derivatives. We're going to know the three conditions of the second derivative for finding the nature of a stationary point. Once you see that, you're going to wish you knew it higher. um, we're going to look at rectilinear motion and what it is, that it's just motion in a straight line, and look at the calculus connections between displacement, velocity, and acceleration. So, for the first part, we're going to take a wee look at the notation for higher derivatives. Okay, so when you differentiate a function, you will sometimes have to or want to differentiate it more than once. So in the case of the stationary points example that we'll look at shortly, you're going to want to differentiate and then differentiate again, and that's called finding the second derivative. So the notation sort of looks like this. The Newton notation for the first derivative, well, this is what you've already seen it higher, f dashed of x and dy by dx. For the second derivative, well, it's sort of common sense for the Newton notation f double dashed of x. And for the Leibniz notation, it's sort of written in a funny way. It's written d2y by dx squared. And that's how it's said, d2y by dx squared, or it can just be called the second derivative. For the third derivative, f triple dashed of x, d3y by dx cubed. Okay. Fourth derivative. Now, Roman numerals are used, so it's fiv of x and d4y by dx to the power 4. And for the fifth derivative, and you sort of get the idea here, f, and we'll use v, the Roman numeral v. So f v of x and d5y by dx to the power 5. Okay, so that's the sort of system for finding higher derivatives at advanced higher. Okay, for the Newton notation, f dash, double dash, triple dash, and then the Roman numerals after. And for the Leibniz notation, just inserting the numbers 2, 3, 4, or 5, or so on, as shown. Right, so that's the notation. So let's have a wee look at this. Let's just put something like that into practice. Let's find all the derivatives of y equal to 3x to the power 4 plus 6x cubed plus 2. So let's start with the first derivative. So I'll just go for f dash of x. Oh no, I can't actually. I shouldn't be doing that because this is written y equals. So I have to use the Leibniz notation dy by dx. So the first derivative is 12x to the power 3 plus 18x squared, and then the plus 2 disappears. So nothing too taxing here. These are expressions that you should be able to differentiate without any issue. Second derivative, d2y by dx squared, is so this derivative is the derivative of the first derivative. So we're differentiating 12x cubed plus 18x squared now. So it's 36x squared plus 36x. Third derivative, 2 36 is 72, so 72x plus 36. Fourth derivative, d4y dx to the power 4. Fourth derivative is just 72. And the fifth derivative is 0. Now, obviously there are no, when we say find all the derivatives, you might be at risk of going on for quite a lengthy time with this. Um, but there are only these derivatives here because, of course, if we went and found the sixth derivative, well, the derivative of 0 is 0, and so on it would go. So what we can do is we can finish it off with a little statement for all integer values of n greater than or equal to 5, dny dxn is always going to be equal to 0. And that just kind of finishes things off as well, and also gives you might get some questions around what this particular sort of integer value of n might be, and some things to think about. So it's a handy wee statement to see. Right, let's have a wee look at not that screen. Let's have a wee look at this one. Find the first four derivatives of y equal to sin x, and hence state the 10th, 12th, and 31st derivatives. So the thing about obviously the trig functions is we know the derivatives are cyclic, so we know that the first derivative dy by dx, we know that that's going to be cos x. This is all from higher. We know the second derivative, just never really used it with this notation. The second derivative is the derivative of cos x, so minus sin x. The third derivative is the derivative of minus sin x, so minus cos x. And the fourth derivative takes you back to sin x. Okay, so that's the first four derivatives. But from that, can we work out what the 10th derivative is? So d10y dx10. Now, if you think about this one, the the derivative, the tenth derivative in the series. Well, we know that this series of derivatives is going to repeat every four derivatives in it. So you're always so like d5y by dx5 is going to be cos x, yeah, the first one in the sequence. So we know that we're going to get this, so we can use the sort of 4 times table to help us find out where we are in the sequence. So d10y by dx10, when you think about it, take those 10 derivatives, divide it by 4, that gives you 8, remainder 2, and the remainder is the part we're interested in. Since the remainder is 2, then d10y by dx10 is going to be the second derivative in the sequence. So the 10th derivative is minus sin x, right? What you don't want to be doing is writing out, a big list all the way up to the 31st derivative and things like that. That's really inefficient. Okay, so let's get the 12th derivative using the same method, d12y by dx12. So the 12th derivative, divide that by 4, and it is, well, since 12 is a multiple of 4, it's always going to be the fourth one, the fourth derivative in the sequence, so sin x. And the 31st derivative, see if you can work it out. But again, if you divide that by if you divide that by 4, 31 divided by 4, you're going to get a remainder of 3, so it's the third derivative in the sequence, negative cos x. So that hopefully sort of gives you a wee flavour. That's something, there's a unit later on in the course called the Maclaurin series, which uses a sequence like this. So we'll study these sorts of things in greater detail much later in the course. Now, let's have a wee look at stationary points. So, like, what's the point in having higher derivatives? It's not going to be useful for anything. Well, for stationary points, and you're going to wish your higher maths teacher had shown you this at higher. You're going to, because it takes away the need to do a nature table, and But at higher, you need to do the nature table because you need to understand the nature of a turning point and how that comes around by inspecting the gradient of the curve left and right at the stationary point and all that kind of thing. So you do kind of need to do it with a nature table, but it can be done with the second derivative. And we tend not to bother showing it to higher kids because it creates confusion. What should I use? When can I use that one? When can I not use that one? Um, and if differentiation is not your forte anyway, then finding the second derivative is never, isn't going to be that easy either. So it's one of those things that we wait until advanced higher really to tell you this. Um, but basically, if you find the second derivative, instead of drawing a nature table, if you take the x coordinate of your stationary point, plug it through the second derivative, and you get a number greater than 0, then that x coordinate is a minimum turning point. If the second derivative is less than 0, then that x coordinate is a maximum turning point. And the last point here is really, really important. If you plug an x coordinate in and the second derivative is 0, then that is a possible point of inflection. And if you get that, you need to go and check it with a table of signs, or in other words, a nature table. You're going to have to go back and do it. So you can't, if you get the second derivative equal to 0, you cannot just say it's a point of inflection and move on, because there's no way of telling whether it's a rising point of inflection or a falling point of inflection, so you will have to justify it through a nature table. Alright, so the last bullet point there is a bummer. If you've gone into all that hassle to find your second derivative and subbing it in and everything like that, and then you find out that you've got equal to 0 and you have to go and do a nature table anyway, then you'd be pretty hacked off, but you know, it's worth doing. So let's have a look at an example of how to use that. So here's um, actually a pretty box standard question from Higher. Find the stationary points for y equals 8 plus 2x squared take away x to the power of 4. So what we got here is our derivative. Let's find, well, we know that to find stationary points we need the derivative, so dy by dx is 4x take away 4x cubed. Okay, so for stationary points, so we're going through all the same process, so we would do it higher for stationary points, dy by dx is equal to 0, so 4x minus 4x cubed is equal to 0. Now we're still not doing anything particularly new here. Factorise and solve this equation. So 4x comes out as a common factor. 1 take away x squared, go in there. And since that's a difference of two squares, we'll keep factorising. We'll get to here, and the solutions are x equal to 0, x equal to minus 1, and x equal to 1. So that's our three x coordinates. I'm finding stationary points, so I better find the y values that go with it. So when x is 0, y is 8. When x is 1, y is equal to 8 plus 2 is 10, take away 1 is 9. And when x is equal to minus 1, y is equal to 10, take away 1, or y will be equal to 9 again. Right, so that's our three coordinates, but we need to find the nature of them. So for nature, we use the second derivative, right? So d2y by dx squared is the derivative of this. So 4 take away 12x squared. Now all we need to do is sub in the three values of x that we have, 0, negative 1 and 1, and evaluate the second derivative. So when x is equal to 0, we'll start with that one, d2y by dx squared is going to be Well, it's going to be 4 take away 12, so it's going to be negative, so we'll just go straight to saying it's less than 0. Now, if the second derivative is less than 0, we can say therefore 0.8 is a maximum turning point. Okay, and so on and so on that goes, right? So we can say when x is equal to, I'll do 1, the second derivative is going to be, oh, actually, I made a mistake with that, didn't I? That was a bit silly. Right, start that one again. Obviously, when x is equal to 0, then that's going to be 4 take away nothing, which is greater than 0. So the point 0.8 is a minimum turning point. Okay, when x is equal to 1, you get a value less than 0, so therefore 1.9 is a maximum turning point, and when x is equal to negative 1, you'll get the same value, so d2y dx squared will also be less than 0, therefore negative 1.9 is also a maximum turning point. So what that does, it sort of just highlights that the second derivative is an acceptable substitution for doing a nature table. So instead of doing 3 nature tables, 3 quick calculations with the x coordinate, the stationary point, and we've got their natures. So it can save you a bit of time, especially if the function or the derivative is quite complicated. Okay, so let's have a little look at rectilinear motion. So just the last wee bit of this. Okay, now basically rectilinear motion is the movement of a particle or body in a straight line. Okay, so no curves or anything like that involved. It's just about a particle or body going backwards and forwards in a straight line. Now I know that not all of you will have done any physics, if any, and I promise you this is the only piece of physics in the maths course. Um, it's there, and you just have to deal with it, I'm afraid. For those of you who aren't doing the physics, you know, even if you've only done sort of National 5 physics, would be enough to get you by through this. But if you've done no physics, then I'm going to go through a little bit of a sort of definitions part with you. So if you've done a lot of physics and physics is something you're pretty good at, you might want to skip on a couple of minutes until I get through this. Um, Basically, what I want to do is go through a term called displacement with you with this example. Okay, so if a man moves 5 meters to the left, oh, that's the wrong way. That's right. If a man moves 5 meters to the left, okay, and then goes 3 meters to the right, okay, then the distance travelled is 5 meters and then 3 meters. So the distance travelled overall is 8 meters, right? But displacement, right? Displacement is a vector quantity, so it's got direction, and so the man's displacement is 2 meters to the left. Yeah, and so that's the difference between distance and displacement. And the reason why I want to highlight that to you is because we're looking at displacement, velocity and acceleration. Velocity and acceleration is pretty common language. You probably got on no bother with that, but displacement less so. So we kind of need to make sure we get a firm understanding of what displacement is, and it is the position of the body relative to where it's kind of started off from. So that's a sort of simple way of thinking about displacement. And if all else fails, you're still not very sure about that, just think of it as a distance. Anyway, and I'm sure that'll probably get you by enough for what we're going to do. So let's have a little look at the calculus connections. So this is the last thing that we're going to take a wee look at. Okay. Now, displacement. We use the letter S for displacement. Don't ask me why, because I actually don't know. But we use the letter S for displacement. And the rate at which displacement changes over time is going to be ds by dt, right? So the derivative of displacement with respect to time. But if you think about how a body would, how its position would change over time, that is linked to its velocity, and they're actually one and the same thing. So this is the first calculus connection to learn, that velocity is the first derivative of displacement. So v equals ds by dt. Okay, and that has to be learnt, folks. The second connection, if we use, not displacement, I should have changed that, we use velocity, right? If we define velocity with the letter v, then the rate at which velocity changes over time is dv by dt. And so, since that's the rate at which velocity changes over time, well, when velocity changes, there must be some sort of acceleration to speed it up or slow it down. So, therefore, the derivative of velocity, so dv by dt, must give you the acceleration, right? In other words, if you think about it, that is the second derivative. So another way of thinking about it might be to say that is the second derivative of displacement, so t2s by dt squared. Okay. Now, let's have a look at a quick example. Now, a particle travels along the x-axis such that s of t equals 4t cubed, take away 2t plus 5, where s represents the displacement in meters from the origin, t seconds after the observation began. Part A is nice and quick. We're going to work out how far from the origin the particle is at the start of the observations, and calculate the velocity and acceleration of the particle after 3 seconds. So this is nice and straightforward, folks, okay? So for part A, well, we have to think about this at the start, and at the start t is equal to 0. So t equal to 0 is what we're going to work with in terms of our calculating a displacement. Okay, so s of t, well, that's going to be, instead of t, it's going to be 0, so s of 0, screen's playing up quite a bit. Right, s of 0 is just going to be 5. Okay, so the displacement of the particle from the origin at the start is 5 meters. Right, nice and easy, nothing too complicated there. Move on to part B. Okay, and calculate velocity and acceleration of the particle after 3 seconds. So t is going to be equal to 3, but we need formulas. Okay, so at t equal to 3, for part B, we just now need expressions for velocity and acceleration. So we've got our expression for displacement, which I'll just write down again, save me flicking up and down the screen. 4t cubed, take away 2t, add 5. There we go. Right, so velocity is the derivative of displacement, so ds by dt. So velocity is going to be 12t squared, take away 2. And so when t is equal to 3, then the velocity is going to be 12 times 3 squared, take away 2. So what does that come to? 106. Now, The units for velocity are meters per second, written like that. So again, apologies, that's one for those of you who haven't done the physics. Let's get an expression now for acceleration. So acceleration equals, now acceleration equals dv by dt. And so the derivative of the velocity there is 24t, and so when t equals 3, the acceleration is 24 times 3, 24 threes is 72, and the units for acceleration are meters per second squared. Okay, so just to kind of quickly recap that, rectilinear motion, remember, is the motion of a particle or body in a straight line, and the idea here is that you are linking displacement, velocity, and acceleration. So if you just remember that order, displacement, velocity, and acceleration, that gives you the calculus process as well. Displacement differentiates to velocity, differentiates to acceleration, and so long as you've got certain values of t, then you can work out the displacement, velocity, or acceleration at a given instant. You could also be asked to find out which value of t gives a particular velocity that might come out to be a quadratic or a cubic equation, for instance. So definitely, definitely a lot going on there. If you need any help or any clarification, please just email me, let me know. Apologies for the last 2 or 3 minutes there being quite rough in terms of handwriting and things. My screen display was starting to act up on me, but it's the way it is. So thanks very much, everyone. Have a good week.